Multiphase flow in high-angle, horizontal, or undulating well bores tends to behave quite differently from multiphase flow in vertical wells. In this presentation, we will contrast flow regimes and logging methods in vertical wells with those in horizontal wells. Here we observe the behavior of vertical flow regimes using clear plastic piping in a simulator designed by the Tulsa University Fluid Flow Project. In reservoirs producing oil above the bubble point, no free gas is present, so the flow regime at the base of the tubing is one of liquid flow. Pressure drops as the oil moves upward. When the pressure drops below the bubble point, gas bubbles form, and the flow regime becomes one of bubble flow. As the fluids continue to rise, the pressure continues to decrease. The bubbles expand, and more gas comes out of solution, resulting in slug flow or plug flow. In this regime, the gas fills the entire tubing cross-section and intermittently carries oil slugs up the tubing. Further up the tubing, at still lower pressures, the gas phase becomes even more prevalent. It now fills the center of the tubing, with an annular ring of oil moving more slowly upward around it. This is referred to as annular flow. Finally, at even lower pressures, the flow is characterized by oil droplets suspended in gas, referred to as mist flow. In vertical well bores, we see a random distribution of oil, gas, and water phases across the well bore. There is no tendency for a particular phase to accumulate along one side of the well bore or the other, except during annular flow, when the gas phase occupies the center of the well bore. We also see phase discontinuities caused by velocity differences between phases, although the phase distribution across the well bore is random. This random distribution of phases enables center sample logging tools to accurately measure the relative flow rate of each phase. In addition to measuring flow rates, the center sample tool design has been used effectively in vertical wells to measure holdup, or the fraction of cross-sectional area occupied by a particular phase within the wellbore. Now, let's examine the flow regimes found in horizontal wells. Flow in non-vertical wellbores behaves differently from that in vertical wellbores. Here, we see phases segregated or stratified by density, with water flowing along the bottom of the wellbore, oil flowing above the water, and gas flowing on top of the oil. In stratified flow, the phases are segregated by density. The lightest phase flows at the top of the wellbore, and the heaviest phase flows at the bottom of the wellbore. The interface between phases may be a dispersed and turbulent mixture of the phases. This regime occurs at relatively low flow rates. If the interface between phases is flat, the flow is classified as a stratified flat flow. When stable waves form on the interface between phases, the flow is classified as a stratified wavy flow. Intermittent flow is characterized by an alternating flow of liquid and gas. Slugs of liquid fill the entire cross-sectional area of the wellbore and are separated by gas pockets that contain a stratified liquid layer flowing along the bottom of the well. The intermittent flow pattern is divided into slug and elongated bubble patterns. Slug and elongated bubble flow behave the same with respect to the flow mechanism, and they are often treated the same in interpretation. Annular flow occurs at very high gas flow rates. The gas phase flows within a high-velocity core that often contains entrained liquid droplets. The liquid flows as a thin film around the wellbore. In the dispersed bubble flow regime, the oil or gas bubbles tend to flow along the top of the wellbore. Undulations in the wellbore tend to further displace the phases as water pools in the troughs, and gas and oil are trapped in the crests. As the phases travel through uphill sections of the wellbore, the velocity of the lighter oil and gas phases increases with respect to the heavier water phase. The opposite behavior is exhibited within the downhill segment of the undulation, when the velocity of the heavier phase increases and the lighter phases slow down. Unlike hold-up measurements in vertical wells, changes in holdups are not proportional to inflow along a horizontal or undulating wellbore. To characterize inflow along a horizontal or undulating wellbore, the wellbore inclination and associated flow regime and phase velocity must be measured along with the holdup. We've seen how non-vertical wellbores exhibit density segregation of phases, as opposed to the random distribution of phases in vertical wells. In the absence of a random distribution of phases, the center sample logging tools used in vertical wells are generally unable to obtain representative hold-up measurements of each phase in a horizontal wellbore. For this reason, each of the 3 leading oil field service companies is developing and refining tools for measuring flow in horizontal wells.